Dear students, now let's start chapter 2, standard 12, electrostatic potential and capacitance. Now, first topic, work done on moving charge in electric field. Now, actually, this particular topic is not given to you in the text in detail, but this one is very important thing. So let's discuss it first. Okay, work done on moving charge in the given electric field. See, suppose here we consider a source charge capital Q which is at the origin of Cartesian coordinate system, and now in the space its electric field is prevailing. Now a small q charge is placed at point A in the Cartesian coordinate system, and now suppose we want to move that particular charge q from A to point B, and in this particular process we will calculate the total work done. Okay, now see here, first we consider the path A to C and then C to B. Now Q to A, this position vector is R1, so the distance Q to A or O to A, that is R1. Okay, so here on the curved path having radius equal to R1, charge small q is moved from A to C. Okay, so first we will calculate the work done on moving charge small q from A to C. So that is q integration A to C E dot dr, because after all E, that is nothing but the force acting on unit positive charge. So in the electric field E, force on charge q, that is q into E, and dr, that is displacement, force into displacement, that is work done. Okay, now here this work done will be zero. Why? Because electric field that is radially outward. So at each and every point on the AC path, the infinitesimal small displacement dr and electric field E both will be perpendicular to each other, and therefore the dot product E dot dr, that will come to zero. So work done to move charge small q from A to C, that is equal to 0. Now move it from C to B. So we can write work done from C to B, q integration C to B E dot dr. O to C, that is R1, and O to B, that is R2. So we can write the limits here are R1 and R2. So this is equal to q R1 R2, and at distance R the electric field, that is kq upon R square into R caret dot dr, the displacement, that is in the direction of the field. So we can write dr R caret dot R caret, that is 1. And here small q, k and capital Q are constants. So we can take the integration of 1 upon R square. Integration of 1 upon R square, that is minus 1 upon R. Take the limits R1, R2, then substitute the limits. First upper limit, then minus lower limit. So this is equal to KQQ 1 upon R1 minus 1 upon R2. Because when we take first upper limit, so minus 1 upon R2, then minus 1 upon R1. So here it is written first. So now total work done on moving charge q from A to C, C to B, that is 0 A to C, then C to B, KQQ into 1 upon R1 minus 1 upon R2. So total work done on the path A to C to B, that is KQQ 1 upon R1 minus 1 upon R2. Now let's discuss another path. Suppose charge Q is moved from A to D and D to B. So work done on moving charge Q on path A, D, B. So first we will calculate A to D. So A, that is at a distance R1, D, that is at distance R2. So as previously calculated from C to B, like that we can write KQQ into 1 upon R1 minus 1 upon R2. And similarly D to B on the curved path, work done, that is 0. So again total work done on the path ADB, that is KQQ into 1 upon R1 minus 1 upon R2, that is from A to D, and then from D to B it is 0. So again we can see the work done on the path A to D to B, that is KQQ into 1 upon R1 minus 1 upon R2. It implies that on both the path the work done, that is the same one. So here the work done that does not depends on the path. It implies that we can say this thing, the electric field, that is the conservative field, or electric force, that is conservative force. Here work done depends only on the initial and final position. The same type of things that we studied in standard 11 in the chapter of gravitation. Gravitational field and gravitational force are also conservative field and force respectively. Clear to all of you? Now next topic, electrostatic potential energy and potential energy difference. Now see here, suppose here we consider the electric field due to charge capital Q, which is placed at the origin of Cartesian coordinate system. And in the field of this capital Q, small q charge is moved from point R to point P against the repulsive force of capital Q. Here capital Q and small q are greater than 0. Okay. Now this work done by the external force against the repulsive electric force, that is W R to P, that is minus integration R to P F external dr. So this is the work done by the external force against the repulsive force of charge capital Q on small q. Now this work done against the electrostatic repulsive force, that will be stored in it in the form of potential energy. Okay. So here we can write the potential energy difference when charge small q is moved from R to P. Then at P the potential energy UP, at R its potential energy is UR. So potential energy difference, that is the work done to move it from R to P, and that is UP minus UR. So here we can write the work required to be done by an external force in moving without acceleration charge small q from one point to another point in the electric field of any arbitrary charge configuration is the potential energy difference between those 2 points. But here if you want to find the absolute value of the potential energy at any point, then the convenient way, that is to consider the value of the potential energy at infinity, that is 0, because we consider at infinity the electric field of any charge distribution, that is 0. So here if we take this point r at infinity, then we can say the work done to move charge plus q from infinity to point P, then we will get the potential energy difference, that is the work done to move charge small q from infinity to P, that is UP minus U infinity. But U at infinity, that we consider 0. So this one is UP. It implies that now we can write the definition of electric potential energy at any point in the given electric field, that is the potential energy of charge q at a point in the field, that is the work done by the external force equal and opposite to the electric force in bringing the charge q from infinity to that particular point. So this is called the potential energy of that charge small q at a given point P. Clear to all of you? Now next topic, that is electric potential and electric potential difference. So in previous topic we discussed this thing, the work required to be done against the field to bring charge small q from infinity to a given point, that is the electrostatic potential energy of charge small q. So here electric potential is defined as the work done against the field in bringing the unit positive charge from infinity to a given point in the field, that is called the electric potential at that point or electrostatic potential at that point. So we can write here electrostatic potential at point P in the given electric field, the work done against the field in bringing unit positive charge from infinity to a given point. So F dot dr, force into displacement, that is the work done. Force that is on unit positive charge and it is brought from infinity to point P against the field, so negative sign is introduced. But force on unit positive charge, as per definition, it is electric field. So we can write electric potential at point P, that is minus integration infinity to P E dot dr. This is the electrostatic potential at point P in the given electric field. So here the electrostatic potential difference between points Q and P. So simple thing, we have to take the potential at Q, then minus potential at P. So we can write VQ minus VP, that is minus integration infinity to Q E dot dr as per this particular definition, minus integration infinity to P E dot dr. So this is VQ minus VP. Now see here, if we change the limit, then in mathematics you studied this thing, if we change the limit, then the sign will be changed. So here integration infinity to Q, that we will take Q to infinity with positive sign. So first step, integration Q to infinity E dot dr. Second one, minus plus. So plus integration infinity to P E dot dr. So here integration Q to infinity, then infinity to P. So combining the limits we can write this is equal to integration Q to P E dot dr. Okay. So we can write it VQ minus VP, that is minus integration P to Q E dot dr. But as per definition we can say this minus integration P to Q. E dot dr, that is nothing but the work required to be take the unit positive charge against the field from point P to point Q. That is the potential difference between points P and Q. Clear to all of you? So here we can write this VQ minus VP, that is minus integration P to Q E dot dr. Now its unit, that is volt, and volt, that is joule per coulomb. Its symbol, that is V equal to J by C, and its dimensional formula, that is M1 L2 T minus 3 A minus 2. Clear to all of you? Now next topic, that is potential due to a point charge. Now here consider a charge capital Q, that is the source of electric field, and in its electric field at point P, which one is at distance R, we want to find the electric potential. Okay. Now for that, as per definition, we have to bring unit positive charge from infinity to this point P, and we have to calculate the total work done against the field in this particular process. Okay. So now here first consider one intermediate point P dash, which one is at a distance R dash. Okay. And now let's calculate the work done to move unit positive charge from P dash to distance delta R dash towards the charge Q, means against the field. So at P dash, the force on unit positive charge, so force, that is Q1 Q2 upon 4 pi epsilon 0 R square, as per Coulomb's law we can write Q1 is capital Q, Q2 is positive charge, unit positive charge 1 upon 4 pi epsilon 0. Distance between these two is R dash, so R dash square, and R dash caret, that is the unit vector in the direction of OP dash. Now calculate the work done against the field to move this unit positive charge from P dash to distance delta R dash. Means it is moved from R dash to R dash minus delta R dash. So delta W, that is equal to Q into 1 upon 4 pi epsilon 0 R dash square. That is the force. Displacement delta R dash caret here for this force, and for delta R dash it is in the opposite direction of the force. So minus R dash caret, so you can write negative sign here, and R dash caret, that is equal to 1. Okay, so directly it is written minus Q into 1 upon 4 pi epsilon 0 R dash square delta R dash. This is the work done to move unit positive charge from P dash to this point. Okay. Now total work done to bring this unit positive charge from infinity to P, so that we can calculate by taking the integration. So W, that is equal to minus integration infinity to R Q upon 4 pi epsilon 0 R dash square dr dash. This is the work done by external force against the field in bringing unit positive charge from infinity to that given point. Okay. Now Q upon 4 pi epsilon 0, that is constant. Integration of 1 upon R dash square, that is minus 1 upon R dash. Limits infinity to R, substitute upper limit, then minus lower limit. So Q upon 4 pi epsilon 0, this negative sign is taken inside. So 1 upon R minus 1 upon infinity, but 1 upon infinity, that is 0. So we can write this is equal to Q upon 4 pi epsilon 0 R. But as per definition of electric potential, this work done, that is called the electrostatic potential at that point. So electrostatic potential at point P at distance R from this source charge V at R, that is Q upon 4 pi epsilon 0 R, or we can write Q upon R. So here, if Q is positive, then potential will be positive. If Q is negative, then potential will be negative. So here we can see this thing for a point charge, the electrostatic potential proportional to 1 upon R. In previous chapter we studied this thing for a point charge, the electric field that proportional to 1 upon R square. Clear to all of you? Now example 2.1. A. Calculate the potential at a point P due to a charge of 4 into 10 raised to minus 7 coulomb located 9 centimeter away. B. Hence obtain the work done in bringing a charge of 2 into 10 raised to minus 9 coulomb from infinity to the point P. Does the answer depend on the path along which the charge is brought? So let's first calculate the potential at point P. Now charge given to you, that is 4 into 10 raised to minus 7 coulomb, and distance of the point from the charge, that is 9 centimeter. So that is 9 into 10 raised to minus 2 meter. Now potential, that is KQ upon R. So substitute the values of K, Q and R. K, that is 9 into 10 raised to 9. Q, that is 4 into 10 raised to minus 7 upon R, that is 9 into 10 raised to minus 2. Solve it. You will get the answer 4 into 10 raised to 4 volt. Now obtain the work done in bringing a charge 2 into 10 raised to minus 9 coulomb from infinity. We know as per definition the potential at a point, that is nothing but the work done to bring unit positive charge from infinity to that point. So for this much charge, the work done is Q into V. So Q, that is 2 into 10 raised to minus 9 coulomb given to you. So we can write the work done W, that is Q into V. Q, that is 2 into 10 raised to minus 9. V, that is 4 into 10 raised to 4. If you solve it, you will get 8 into 10 raised to minus 5 joule. Now the question is, does the answer depend on the path along which the charge is brought? No, because electric field, that is conservative field. So work done that does not depend on the path, it depends only on the initial and final position. Clear to all of you? Now next topic, potential due to an electric dipole. Now see, suppose we have the electric dipole as shown in the figure. Charge is plus Q minus Q separated by distance to A. This is the center of the dipole O, and from the center of the dipole point P, that is at position R. So this one is at position R. Now we want electric potential of this dipole at point P. Okay. So simple thing. First of all, we have to take potential at P due to plus Q charge, then potential at P due to minus Q charge. So from plus Q, the distance of P, that is R1, and from minus Q, the distance of P, that is R2. So for a point charge, we have the potential, that is KQ upon R. As per that, we can write V1, K, that is 1 upon 4 pi epsilon 0, Q upon R1. And V2, that is Q is negative, so minus 1 upon 4 pi epsilon 0, Q upon R2. So resultant potential at P, that is V1 plus V2. So we can write 1 upon 4 pi epsilon 0 Q upon R1 minus 1 upon 4 pi epsilon 0 Q upon R2. Now here if we take Q upon 4 pi epsilon 0 common, then we can write V, that is Q upon 4 pi epsilon 0 1 upon R1 minus 1 upon R2. But here we have the distance of that particular point, that is with respect to center of the dipole. So we have to represent this R1, R2 in terms of R. Okay. Now see here. Suppose we consider this position R1 as a position vector R1. Then here A vector is like this and this is our R vector. Okay. So if we take opposite vector of A like this, then we can write this is minus A. Okay. So that will be somewhere here, we can extend it up to this one. So we can say the angle between R and A, that is this one, and that will be 180 minus theta. And now we can say vector R1, that is this plus this, okay, as per vector summation rule. So magnitude wise we can write R1 square, that is R square plus A square plus 2AR cos pi minus theta. Clear to all of you? Now similarly here, suppose we think about this R2, then vector R2, that is like this one is vector R, okay, and if we take here, this one is vector A, then vector A plus R, that is vector R2 as per vector summation rule. So here angle between R and A, so you can extend this A from this one like this, so angle is theta. So you can write here, see R1 square cos pi minus theta, that is minus cos theta, this one is simplified. But now for R2 square you can write R square plus A square plus 2AR cos theta. Okay. Now see here, take R square common. So R1 square equal to R square into 1 plus A square upon R square. Here 1 R is there, so minus 2A cos theta by R. Similarly here also you can take R square common. So R2 square equal to R square into 1 plus A square upon R square plus 2A cos theta by R. Now R is very much greater than A. So we can neglect A square upon R square in both these equations. So we can write R1 square, that is nearly equal to R square into 1 minus 2A cos theta by R. Similarly here, neglect A square upon R square. So R2 square, that is R square into 1 plus 2A cos theta by R. Clear up to this one? Now take square root on both the side. So R1, that is R into 1 minus 2A cos theta by R raised to 1 by 2. Here also R2, that is equal to R into 1 plus 2A cos theta by R raised to 1 by 2. We want 1 upon R1 and 1 upon R2. So take reciprocal of this one. So here 1 upon R1, that is 1 upon R into this one 1 upon this raised to 1 by 2. So directly we can write 1 minus 2A cos theta by R raised to minus 1 by 2. Similarly directly here also we can write 1 upon R2, that is 1 upon R into 1 plus 2A cos theta by R raised to minus 1 by 2. Now let's use binomial theorem and then retaining term up to the first order and neglecting higher order terms. We know this thing. So we can write here 1 upon R1, this raised to minus 1 by 2, that will be in multiple with the second term. So 1, this minus 1 by 2 into minus plus 2 cancel. So A by R cos theta. Similarly here 1 upon R2, that is equal to 1 upon R into 1 minus A by R cos theta. Now we have 1 upon R1 and 1 upon R2. Now substitute these values of 1 upon R1 and 1 upon R2 in this equation 1. Okay. So we can write now here 1 upon, V equal to Q upon 4 pi epsilon 0, 1 upon R into 1 plus A by R cos theta minus 1 upon R, 1 minus A by R cos theta. Now if we take 1 by R common here, then we can write Q upon 4 pi epsilon 0, 1 upon R, this 1 plus A by R cos theta minus 1 minus minus plus A by R cos theta. Now this 1 will be cancelled. A by R cos theta, A by R cos theta 2 times. So Q upon 4 pi epsilon 0, 1 upon R, 2A cos theta upon R. But Q into 2A, that is called the dipole moment P. So we can write V, that is equal to Q upon 4 pi epsilon 0, 2A cos theta, R into R square, and 2A into Q, that is P, the dipole moment. So we can write 1 upon 4 pi epsilon 0, P cos theta upon R square. So here P cos theta, that you can write P dot R caret also, where R caret is the unit vector along the position vector OP, means center to the point where we are calculating the electric potential. In that direction, you have the unit vector R caret, because this cos theta, here this theta is the angle between dipole moment and the position vector. So unit vector is in the direction of that position vector. Okay. So we can write potential at point P, that is 1 upon 4 pi epsilon 0, dipole moment vector P dot R caret upon R square. Here we consider this thing, R is very much greater than A. Now, if theta, that is equal to 0 here, then potential will be 1 upon 4 pi epsilon 0 P upon R square. If your theta, that is pi, then cos pi minus 1, so V, that is minus 1 upon 4 pi epsilon 0 P upon R square. And if theta, that is equal to pi by 2, then V equal to 0. Theta equal to pi by 2, that is the point on the equatorial line. So on the equatorial line of electric dipole, at each and every point, the electric potential, that will be equal to 0. Remember this thing, that is very useful for problem solving and MCQ solving. Now, here we have the electric potential at a point due to electric dipole. And here we can see this thing, the electric potential that not depend only on the distance R, but it also depends on the position of the point with respect to dipole, or we can say dipole moment, because here this cos theta appears. And here we can observe this thing, the electric potential of the dipole that decreases as 1 upon R square. And in previous theory we discussed this thing, the electric potential due to a point charge that decreases as 1 upon R. Clear? So this one is the electric potential due to dipole. Clear to all of you? Now next topic, that is potential due to a system of charges. See, suppose we have a system of n charges Q1, Q2, Q3 up to Qn. having position vectors r1, r2, r3 up to rn with respect to the origin of Cartesian coordinate system. And we want to find the electric potential due to this entire charge distribution. This is the discrete distribution of charges at point P having position vector r. Very simple thing. Here we can use superposition principle. We have to find the potential at P due to each and every charge, and then after we have to take summation of it. Suppose we think about the electric potential at P due to Q1, so that is 1 upon 4 pi epsilon 0 Q1 upon distance between 1 and P, so that is magnitude vector r minus r1. Similarly, potential due to Q2, Q3, Q4, that we can write as V2 equal to 1 upon 4 pi epsilon 0 Q2 upon R2P, V3 equal to 1 upon 4 pi epsilon 0 Q3 upon R3P. This is the distance of the point from the respective charge up to Vn equal to 1 upon 4 pi epsilon 0 Qn upon Rnp. Now simple, we can use the superposition principle and take the summation of all these. So we will get the resultant potential at P. But here be careful, we have to take algebraic summation. It implies that out of this entire distribution, if any one charge, one or more, any charge is negative, then its potential will be negative one. So in summation we have to reflect it. Now resultant potential at P, that is V1 plus V2 plus V3 up to Vn. Now we can take 1 upon 4 pi epsilon 0 common from all these potential equation. So we will get Q1 upon R1P plus Q2 upon R2P up to Qn upon Rnp. So we can write V, that is equal to 1 upon 4 pi epsilon 0 Q1 upon R minus R1 magnitude plus Q2 upon magnitude R minus R2 plus up to Qn upon magnitude R minus Rn. Clear to all of you? Dear students, now next topic, that is electric potential due to volume distribution of charges. Suppose in a particular region the distribution of charges that is given to you, and this particular distribution, that is continuous distribution. So in previous chapter we studied about the electric field due to continuous charge distribution, right? So here we can easily understand how to calculate this potential. Here what we have to do, we have to use the concept like this. We have to divide this continuous charge distribution into so many infinitesimal small volume elements. Then we have to find the electric potential at a given point due to each infinitesimal small volume element, and then after we have to take the summation of all those potentials. So here suppose we consider one small volume element d tau dash, which one is at position r dash, and suppose the volume charge density, that is rho, at position r dash. Now volume charge density means charge per unit volume. We considered the volume, that is d tau dash. So per unit volume the charge is rho, then in d tau dash how much? So now charge in that particular small volume element, that is rho at r dash d tau dash. Now due to this particular small charge, what is the potential? So we can write that potential dV, that is 1 upon 4 pi epsilon 0 Q upon R. Q, that is what? So charge in that particular small element, that is rho at R dash d tau dash, upon the position of that particular point with respect to that volume element. So we can write that is magnitude R minus R dash. Now, if entire charge distribution is divided into so many small volume elements, and then we find for each one the potential like this, and then if we take the summation. But here the volume elements are very small, we can consider it tends to 0, and the distribution is continuous one. So we can calculate this total potential with the help of integration of this equation over the given volume. So potential at a point having position R, that is 1 upon 4 pi epsilon 0, integration over the entire volume distribution, rho at R dash d tau dash upon R minus R dash. So here, if the charge distribution, that is uniform one, and the volume charge density, that is constant one, then except taking rho at R dash, simply you can consider it as rho. Clear to all of you? Now next topic, that is electric potential due to uniformly charged spherical cell. Suppose, as shown in the figure, we have uniformly charged spherical cell. Total Q amount of charge is uniformly distributed on this particular cell. Radius of the cell, that is capital R. Now suppose we want potential at a distance small r from the center of the cell, where small r, that is greater than capital R. It implies that we want potential due to this uniformly charged spherical cell at any point outside the cell. So in previous chapter we discussed about the electric field of this type of charge distribution, and in that we studied this thing. This entire charge distribution behave like a point charge concentrated at the center. It implies that this entire Q charge distribution behave like a point charge at the center. So due to a point charge, the potential at a distance r, that is Q by R, or you can write 1 upon 4 pi epsilon 0 Q by R. So we can write V, that is equal to 1 upon 4 pi epsilon 0 Q by R. Clear? Now suppose we consider a point at the surface of the cell. Then at the surface of the cell, the distance from the center, that is capital R. So we can write the potential at the surface, that is 1 upon 4 pi epsilon 0 Q by R. Clear? Okay. Now if we want potential at any point inside the spherical cell, means this distance r, suppose we take less than capital R. Now up to this one, we have the work done to bring the unit positive charge from infinity to this point, that is Q by R, because that is the potential at the surface. Now if you want to find the potential at this point, means we have to calculate the total work done in bringing unit positive charge from infinity to this point. But up to this one we have already calculated. So now we have to calculate the additional work done to move unit positive charge from surface to this point. But now the important thing is this one. In previous chapter we studied inside the cell electric field is 0. So when electric field is 0, then work done to move unit positive charge from surface to any point inside the cell, that is 0. It implies that here the potential at the surface KQ by R, that will remain constant up to the center. So we can say the electric potential at any point inside the spherical shell, that will be 1 upon 4 pi epsilon 0 Q by R, or we can write KQ by R, for R is less than or equal to capital R. So inside the cell, at each and every point, the potential that is constant one, and that is KQ by R. Clear to all of you? Now example 2.2. Two charges 3 into 10 raised to minus 8 coulomb and minus 2 into 10 raised to minus 8 coulomb are located 15 centimeter apart. At what point on the line joining the two charges is the electric potential 0? Take the potential at infinity to be 0. Now see here the situation given to you, that is like this. Two charges Q1, Q2, that is 3 into 10 raised to minus 8 coulomb, and Q2, that is minus 2 into 10 raised to minus 8 coulomb, which are separated by distance 15 centimeter. Okay. Now here, at what point on the line joining the two charges is the electric potential 0? Now that we want to find. So here electric potential, that is the scalar quantity. For positive charge, potential is positive. For negative charge, the potential is negative. So here you will get 2 points where the net potential will be 0. One point will be between two charges and another point will be outside these two charges. But outside these two charges, that point will be close to the smaller charge. So magnitude wise smaller is this one. So outside these charges, on right hand side here you will get another point. Now suppose one point P, that is at a distance x from charge Q1, where the potential becomes 0. It implies that from charge Q2, it will be at a distance 15 minus x. So net potential at P, that is V1 plus V2, that is KQ1 upon R1 plus KQ2 upon R2, that is equal to 0. Now let's substitute the values. Okay. Take K common, take it on right side, will be cancelled. Now here K cancelled, values 3 into 10 raised to minus 8 for Q1 upon distance x. Second charge, that is negative, so minus 2 into 10 raised to minus 8 upon 15 minus x, that is equal to 0. K take on right side, cancelled, 10 raised to minus 8, 10 raised to minus 8 will be cancelled. So you can write 3 by x, take this one on right hand side, so equal to 2 upon 15 minus x. Now here we have to make x as a subject of equation. So first take cross product and then after make x as a subject. You will get the answer x equal to 9 centimeter. Means one point obtained between two charges at a distance 9 centimeter from charge Q1, where the net potential of the system comes to 0. Now second point, that will be outside this one. Okay. Suppose the second point is at a distance y from the Q1. So it will be at a distance y minus 15 from Q2. From figure easily you can understand. So here again, as per this equation, we can write K 3 into 10 raised to minus 8 upon y minus k 2 into 10 raised to minus 8 upon the distance y minus 15. K 10 raised to minus 8 will be cancelled. Take this portion on right hand side. So 3 by y, that is equal to 2 upon y minus 15. Now take a cross product and then after make y as a subject of equation. You will get the answer 45 centimeter. Means the second point where the net potential of the system is 0, that is at distance 45 centimeter from charge Q1, or we can say that is at distance y minus 15 means 45 minus 15, that is 30. So at 30 centimeter from charge Q2. Clear to all of you?